Okay. We are now ready for the second part of the White Bandgap Podium's discussion. I see ladies and gentlemen again here, and I see nearly every chair is occupied, and so we can start. We have a simple way this time, which just start from over there. Alex will be the first, and then we go around here. But we can mix it up. We can start in the middle. However, the presenters like it best. Okay, here we go. Alex, it's your... What? Warum? Alex ist der links.
Do you testament?
Okay.
We decide I will start.
Okay. I was not fully briefed. Sorry for the confusion. At least nothing get lost.
No problem. Okay. Does it work now? Yeah. Hello? Yeah. Okay. Good afternoon, everyone. My name is Carlos Castro, and I'm responsible for GaN at Nexperia. And today I will give you an overview why we believe at Nexperia that GaN is already prepared, already ready for mainstream applications and markets. But let me start giving you a short overview about the Nexperia GaN program. We started releasing products in 2019. It was our first generation based on a TO247 package. And then 1 year later, we released the second generation. This year, we are releasing the second generation, but in a different package. I think we all agree that GaN has great benefits in the application in terms of, power density, efficiency, but as well system cost. But if you want to get all the benefits of GaN in the application, you need as well a package which is not limiting those benefits. And that's why we have developed the CC pack, which give us as well huge potential for getting all the benefits of GaN in the application. And next year, we are expecting to release as well the next generation, for us, the third generation of GaN, and then starting to offer as well an automotive version of it. In terms of markets, we see huge potential in industrial application above 1 kilowatt, and those are things like power supplies for data centers, servers, but as well UPS, solar inverters, and even in audio amplifiers as well. And of course, in automotive, we see as well huge benefits of GaN, and we see already a lot of projects and activities going on in automotive, mainly for applications like onboard charger, but as well long-term, we see already activities for the main inverter as well. Now, why do we believe that GaN is already there to stay, but as well not only for niche applications, but for mainstream applications? Of course, because GaN is GaN on silicon, and that offers us a lot of benefits in terms of manufacturing and cost reduction potential. It's a simple process, easy production. We can scale up quite easily and have the volumes, and as well because of the supply chain is an established supply chain. So those are benefit in terms of potential cost reduction. And in terms of performance, we we concentrate on a D-mode technology with a cascode configuration. We believe that for some applications, it offers clear benefits in terms of performance, being more efficient, lower losses, but as well very easy to drive. And I will go a little bit more in detail as well through that in the next slide. But as well a technology which is very robust and reliable. And we have transient voltages capability higher than the DC voltage. The gate voltage as well goes from -20 to 20 volt. The threshold voltage is 4 volt. So all things that most of you know from silicon technology, and you don't need to adapt anything in your design that much in terms of topology, and we can as well go into an ACQ qualification with this, an automotive qualification with this technology. And then what I mentioned it before is the package. I mean, I think we all agree that it doesn't make sense to have a Ferrari engine on a Fiat 500. That's like we do sometimes with silicon carbide and gallium nitride. I think it is really needed to have proper packages for those technologies so that you can get all the benefits in the application. And that's what we have done with the CC pack, which is a kappa clip design, very robust, very reliable, offering top and bottom cooling, and really designed for high voltage and high power applications. Now, why do we believe Cascode is helping us to be an enabler for mainstream application? One is what I mentioned it before. It's easy to drive. We have a threshold voltage of 4 volts, and that means that we can eliminate the risk for parasitic turn on in very high current, high power applications. And it's something that everyone more or less know from the silicon world, but as well the efficiency, not only the conducting losses, but the switching losses are really very low. And then what is maybe important in some applications, maybe not in all, but in some applications, is the fact of having with D-mode technology a much lower losses in the third quadrant compared to other GaN technologies and compared to SiC. And that means that in those dead times, you can significantly reduce the losses, which could be critical as I said, in some applications, mainly where you have very high frequencies. And then something which I think it's overall for GaN, not particular for Nexperia, but it's the fact that we can definitely reduce the system cost in the application. And what I'm showing here is just an example with an onboard charger where we are comparing the cost with silicon carbide and GaN, and mainly because of the reduction of cost in passive components, the overall cost can be reduced significantly. And then about the package, I just wanted to highlight a little bit the details of what we believe it is really important for GaN to have. We have at Nexperia over 20 years of experience in kappa clip innovation, and that's what we are applying now to GaN, being a kappa clip technology with really, really low inductance, strong inductance, but as well RDS on, and as well the performance in terms of RTH, thermal performance. We offer top and bottom cooling, and it's a product which has been designed for volume, for manufacturing, and to be qualified as well automotive. Last but not least, I just wanted to give you an overview where we are focusing in terms of applications and markets. For power level, we are concentrating on those applications above 1 kilowatt. And as I said before, those are things starting with audio amplifiers and telecom, industrial applications, servers, data centers, automotive DC-DCs, onboard chargers, and even to traction inverters. For voltages, we believe the sweet spot for GaN will be in the 650 volt. We could extend that to 900 volt, and meanwhile we have that as well in our roadmap. But we strongly believe for now the sweet spot is in the 650 volt. For 1200 volt devices, or I should say for 1200 volt topologies, we are working with some customers in projects using topologies which allow us to use as well 650 volt devices using things like multi-level inverters. And for packaging, as I said before, we use TO-247 like everyone is using, but we recognize that we need something else much more appropriate for GaN and the performance of GaN. That's the CC pack. We offer as well bare die. We work with customers working with power modules, and we have as well some collaborations there. So that's all I have for today. Now very happy to answer the questions, and as well, of course, after the presentation, if you prefer to discuss one-to-one in our booth, as well, very happy to answer your questions.
Thank you, Carlos.
Okay. Good afternoon. Thank you, Bodo, for inviting me. Always good to be here.
My pleasure.
Okay, I'm going to talk a little bit about wide bandgap use in power converters. Of course, I don't need to explain that there are benefits to wide bandgap, so I won't go into that. What I'm going to talk about is how to get the most out of the wide bandgap technologies. It's one thing to have a device, it's another thing to get the best performance in a power converter. And the key to that is integration. So this is our InnoSwitch product. You can see that it integrates both the primary side and the secondary side, including the switch on the primary side, and it drives the synchronous rectifier on the secondary side. And it comes in a surface mount package that you see there, and it basically integrates so many of the components that you reduce component count by more than 70 components. It's a very significant integration. In terms of what we have integrated, we have the primary device, which could be a silicon or any wide bandgap device. In fact, we offer both GaN and silicon carbide. We offer GaN up to about 200 watts and 750 volt rating. And we offer silicon carbide up to 1700 volts for both automotive and industrial applications. The beauty is the circuit looks exactly the same. It doesn't matter what power converter you build. And that's because we take care of all of the intricacies of driving the GaN and silicon carbide. Both of them are different technologies. It takes different techniques to drive them optimally so that you get the best performance in terms of efficiency. But at the same time, you don't generate too much noise. I mean, GaN, as you know, can switch very fast. And when it came out first, everybody started going at very high frequencies and suddenly realized that's not very optimum because the rest of the system gets very inefficient, especially the transformer. So what we have done is we have optimized each and every one of our devices to give you the best efficiency with the least amount of DVDT or noise and make it very easy to use. It's fully protected, which is, again, very difficult to do with GaN because it's so fast, it kills itself before you can protect it. And we do that in a lossless fashion, so you don't have to add an external resistor. We also have completely current-driven supply voltage, so you don't have to worry about what output voltage is. You don't have any linear regulators in powering the device. We have lossless current sensing. We have lossless voltage sensing of the input voltage. It's not shown in this diagram, but we can sense the input voltage without loss. The other beauty is it's completely cycle-by-cycle control and doesn't require any compensation at all. Whether it's DCM mode or CCM mode, it is unconditionally stable. Of course, the most important is it simplifies the design. You don't even have to know that it uses silicon or GaN or silicon carbide. It looks exactly the same from a system design point of view. In fact, if you look at the waveforms, you couldn't tell the difference. The only difference you'll see is that when you go from silicon to GaN, the efficiency goes up significantly. And when you go to silicon carbide, of course, you get very high voltages, and also you get much better efficiency than you can get with silicon. This is our 1700 volt silicon carbide auxiliary power supply chip. Again, it's the same switch. And this can operate from 50 volts to 1,000 volts. And this is one of the advantages of switch is that it really doesn't care what the input voltage is, all the way down to about 30 volts or so. So we can handle that wide range of input with no problem. If you use any other solution, you have to have some kind of a boost circuit to provide power to the chip. So, we talk a lot about wide bandgap, but silicon still has a place, especially at very low power levels. It's actually very hard to make GaN or silicon carbide small enough to be able to provide the right kind of cost and performance. So up to about 30 watts or so, we use silicon. After that, we transition to GaN, all the way up to several hundred watts. But if you need really high voltage, if you go beyond 1,000 or 1,200 volts, silicon carbide is actually more cost effective. So we use whatever technology is necessary to provide the performance. So technology is just a means to an end, not an end in itself. But the biggest benefit is the integration. When you integrate, you can optimize for each and every power level and for each and every application, and it's totally transparent to the user. Well, thank you very much. Happy to answer any questions you might have.
Thank you, Balu.
All right, well, let's go. First of all, I'll talk about something that none of the others will talk about, and that's lower voltages. All our products are 400 volts and under. And today I'm just going to talk about one specific application. GaN, we've been in production for 12 years. And our GaN products initially went into high volume with LiDAR applications, and then followed by DC to DC, mostly for servers and enterprise computing. And then the third large volume application was actually space level satellites. And now I'm going to talk about the fourth major market for low voltage GaN, and that's motor drives. So let's talk about e-mobility, which is a target market for ours that we've seen a rapid adoption recently. And first of all, it's e-bikes. The reason is that, if anybody has an e-bike, you know that you still want the electronics to be smaller, to fit inside the column. You want it to be lighter. You want it to have a longer range, or you want it to have a cheaper battery, one or the other. So this is a target market for us. Second one is drones. It's pretty obvious that you want things smaller and lighter in drones, and you want to fly farther with higher efficiencies. So those are the markets, and I'll now tell you why GaN is being rapidly adopted there. So in all of these, the motor that's used is a brushless DC motor. And we're seeing, by the way, beyond e-bikes and beyond drones, we're seeing more and more things becoming unplugged. Today you can get, vacuum cleaners that are electric, you can get lawnmowers that are electric, you can get all your tools that are cordless, and they're all going to somewhere around 48 volts, maybe 36 to 26 volts. And they all use brushless DC motors. And so what are the benefits? Well, first of all, it starts off with the fact that GaN has zero reverse recovery, no diode in it. Now that's true for enhancement mode GaN. It's not true for cascode GaN devices, but for enhancement mode, and I believe all the low voltage ones will be enhancement mode, there is zero QRR. And what that means is that you can actually do some marvelous things with brushless DC motors. First of all, you can go to higher frequency switching. Traditionally, these motors have been switched at about 15 to 20 kilohertz. Go up to 100 kilohertz, and I'll show you why that's important. The minute you do that, you actually transition from needing electrolytic capacitors down to needing only ceramic capacitors. Big space savings gives you an extended temperature range and of course much greater reliability and lower cost. So this has been a boom for the adoption of GaN, is the elimination of those heinous electrolytic capacitors. But also with lower dead time, because you have 0 QRR, you can crank down the dead time. And the dead time is a distortion factor. It's a distortion factor in Class D audio. It's a distortion factor in motor drives. In motor drives, that distortion turns into both acoustic noise and a counterforce at the shaft. So what happens when you eliminate that distortion is not only does the motor actually become silent, but you deliver more torque to the motor. And that's an important advantage that actually translates into greater distance. So this, as you can see, motor efficiency goes up, the system becomes smaller, then you can go to smaller size and weight as well. So this is creating a whole new way of doing brushless DC motors for stuff between 96 volts all the way down to 12 volts. Now, EPC's been doing this for quite a while. We started off with discrete components. Our early discrete components aren't even shown here. These are the discrete components that are now widely used in motor drives. So it's a single transistor. You'll notice up at the top, there's some that are actually packaged. Most people know that I hate packages, but I hate this one less. It's a good package. It has almost no inductance in it, and it also has an exposed back surface, so it's very, very thermally efficient. We started our trek on motor drives with monolithic half bridges. That's something you can't do in silicon very easily. These parts were the early ones that were adopted into mostly robotic applications and have become very popular there. And then more recently, monolithic devices, such as that fully integrated power stage that you see in the bottom. Balu mentioned that the advantages of GaN are amplified with integration. That is true. In our case, it's monolithic GaN integration, and we put all the functions of a power stage onto one chip, all in GaN. The upper devices are actually, there are two devices that match up. One is a high-side device that has in it drivers and a level shifter and also a low-side driver. So all you have to do is buy a discrete device for the low side, and it allows you to make a full half bridge with just two components. And the reason for this is that these are very large chips. So it allows you to go up to 65 ampere per leg motor drive applications. This is just an overall impact statement. In this case, it's a MOSFET inverter compared against a GaN inverter. And this is just showing the input inductance. We used only ceramics. We had no input inductor filter. And the torque was higher. The efficiency was higher, and I want to point you to a number a little bit higher up. Note that the input and output powers are different, but the efficiency is the same. So when people talk about the efficiency of a motor drive, they usually talk about the inverter itself, but that's not where the benefit comes from. The benefit comes from how much power can be digested by the motor, and that's why we get about 10% higher efficiency and 10% higher torque delivery. And if you didn't measure it at the shaft, you wouldn't know that. So there's a benefit, and we've shown that there's higher overall efficiency, or there's lower EMI. I didn't show you those charts, but as you go to higher frequencies, your EMI actually reduces. You have lower audible emission, and it's really noticeable. You can make a silent motor. That noise that you hear in a brushless DC motor is the sixth harmonic, which comes from the dead time in a MOSFET. You get lower torque ripple. And at high frequency, your torque ripple goes down proportionately. And finally, all that translates into much smaller size. So this is the next big application that we're seeing. Thank you.
Thank you, Alex.
Right, hello everyone. My name is Llew Vaughn-Edmunds. I'm the Senior Director of Marketing at Navitas. I am going to show you 4 slides very quickly, just on a quick introduction of Navitas and our path into higher power. So, let's start. So Navitas is the industry leader for GaN power ICs. We've shipped over 50 million pieces, and we are in all the mobile charger OEMs, including Samsung, Dell, Xiaomi, Vivo, and LG. We're in over 170 production chargers in the market. We have got 240 chargers in development, which is additional. And additionally to that, we have 0 GaN-related failures. So we have 0 failures. We've got 50 million pieces shipped, and we are the leaders in the GaN power IC. So just a quick slide of the history of Navitas. It was founded in 2014, offering the first GaN power IC. And this is where Navitas differentiates from discrete GaN devices, HEMTs. What we do, what Navitas's success, comes from integrating the driver with the power stage monolithically. So we put the control, the drive, the protection on side of the actual power stage. So with a discrete GaN device, the gate is very sensitive. It has a low threshold, so I mentioned this before. What we do is help the design engineer and the system to overcome that by putting the protection and the control around that gate area. Bear with me. Is that working? Okay. So as you can see, 2014, we IPO'd on the NASDAQ the end of last year. You can see all the OEMs we've been designed into production. We recently launched the GaNSense part, which is the same as our GaNFast, which is a monolithic drive and power stage, but we also put additional sensing and autonomous intelligence into these devices. And if you come to our booth later in Hall 9, we can talk a little bit more on the details of GaNSense and its benefits. Whoops. Okay, so Navitas, this is our first time at PCIM. We're very excited to be here. This is our first message to the market that we're getting into higher power. We're number one in the consumer and the GaN chargers. Now we're going into higher power. We have the first GaN IC design center dedicated to electric vehicle design. And also we opened a new design center focused on data centers. So we're looking at this 1 kilowatt plus power range. That's Navitas's new focus. And this is why we're at PCM, to tell everyone about this. The new part number, the NV6169, is a 45 milliohm designed for 1 to 3 kilowatt applications. And this is the first step into higher power, as I was saying. Now, what Navitas has done is offered a 20-year limited warranty to all our released devices. So typically, power devices will offer you a 2-year warranty. What we're offering is 10 times that. We're offering you a 20-year warranty. So we're putting the statement out there that we're very confident to get into higher power. We have got over 210 billion field device hours. We feel we are ready for the higher power, and these are the statements we're putting there. And then the last slide is that we created a sustainability report which quantifies the positive impact of GaN versus legacy silicon devices. We have this at our stand as a brochure. You're welcome to take some. I think the key message is that for every GaN Navitas GaNFast IC, we can save 4 kilograms of CO2 compared to a comparable silicon device. And if we transform the world to GaN, electrify everything, then we can save 2.6 gigatons of CO2 by 2050. And I think that's that. Thank you very much.
Thank you. questions at that point?
Good afternoon, everyone. My name is Philip Zook. I'm the Senior Vice President of Technical Marketing, Applications, and Business Development for Transphorm. Appreciate you all coming down to hear my presentation. So Transphorm is the only pure-play, publicly traded, vertically integrated GaN company in the world. Based on this structure, the last semiconductor company to actually go public was Cree. That was 23 years ago. So that says quite a bit about our innovation and our capability. But based on this structure and based on our business strategy, 3 areas of our business strategy gives us the ability to do licensing. This actually helps the adoption of GaN. Government funding, this helps us to grow our technology and innovate our technology, and also create different verticals besides our power electronics, our revenue. So, for example, our epi vertical, which is a small part of our business today, but we currently sell into the Department of Defense, Office of Naval Research specifically. It's an $18.5 million contract, but we can also help satisfy commercial customers as well with GaN on silicon carbide, or GaN on sapphire. So all of this helps us to not just enable or enhance our technology, but also innovate. Innovation is critical for basically for the success of an organization. So one of the other things I'd like to talk about is, just in my experience in the semiconductor field, owning a fab or being a part owner of a fab, as we are, was typically seen as a negative, especially from investment analysts. But now, with the huge demand of semiconductors and the short supply, being part owner of a fab, owning your destiny and owning supply chain, actually kind of look like a hero. So having this, supply chain as part of our strategy is definitely a benefit for the organization. So with respect to today, where we're at is we're selling technology anywhere from power adapters, chargers, gaming power supplies, all the way up into mission-critical solutions such as server, network, and storage, data center power supplies, crypto mining, Bitcoin, and blockchain power supplies, as well as defense and aerospace. This spans from 45 watt through about 4 kilowatt today. And it says a lot with respect to what we offer in basically with our vertical integration, owning our GaN FET technology, as well as offering best-in-class reliability. So when we talk about reliability, that is a core function or the foundation of Transphorm. And this is important. So our reliability today sits at over 40 billion hours of field reliability data with a fit rate of less than 0.3 failures per billion hours. So this actually really gives us credence with respect to being able to operate in these different power levels, because from what I know today, we're the only high voltage GaN supplier in volume production above 500 watts. So 650, 900 volts, and also JEDEC ACQ 101, and then I'll talk about our recent 1200 volt as I move forward. So before I get into that, innovation is key to the success of our business. If we don't innovate, we're going to fall behind, and that's not what I plan to do. So the bottom line is what we've done over like last year, we actually displayed or we demonstrated short circuit protection. We were actually displayed 3 microseconds, 180 amp, 3 microseconds at 400 volts. This year, we actually took the design and we actually evolved it some more. We actually took that 3 microseconds, dropped it down to 1.5, and bolted it to a off-the-shelf gate driver, which our technology is agnostic to all gate drivers in the market, with a desaturation function. What we did here is basically drove it to short circuit 120 amps. Basically, it was detected at 500 nanoseconds and a soft shutdown in 300 nanoseconds. So overall, from start to stop, 800 nanoseconds with a 1.5 microsecond short circuit with hold time. We did this 100 times, and then we did a pre and also a post analysis of the device, and did not see any degradation. So as we continue to evolve this technology, this is something that is, we don't have any devices planned for today, but is a technology that we are going to use into the future. And I've heard in the past that GaN would never see 1200 volts. Well, first one here to stand to tell you that we actually demonstrated 1200 volt technology. We demonstrated this technology against the latest and greatest silicon carbide device, and you can see it performs well. We were actually able to achieve similar performance to our Super GaN Gen 4 and Gen 5 technology, operating at 50 kilohertz at 99% efficiency, over 99% efficiency. And as Balu said, it's not the frequency you're running it at, it's the actual intrinsic value of the device and how fast it's running within the device. 2 to 4 times faster than silicon and silicon carbide. So having 1200 volts in our portfolio, 650 through 1200 volts, now expands our TAM even greater to the billions of dollars that it is today. Gives us into the 3-phase market, gets us into the automotive, the 800 volt market that 70% of the automobiles plan to be at 800 volt batteries by 2027, and we're poised for positive growth into this market. So that's my presentation. Thank you very much. If you have any questions.
Thank you.
Thank you. And thank you all for staying and listening. I'm happy to present here. I am the last on this session, and my name is Tamara Baksht. And in this gallium nitride next level design, we have been asked for next level. I can see that next level for gallium nitride will be high power inverter. I firmly believe in electrification of cars. You all know that we are going there. And I believe that gallium nitride will enable these electric cars of the future. We had seen low power motors kindly presented by Alex Lidow. It's a great product. For gallium nitride, it's very great to have high efficient motor. It's also nice to have high efficient inverter, especially when we are talking about 80 kilowatt, 100 kilowatt, 200 kilowatt inverter. And rationale for this, as you can know, that we have here high efficient inverter essentially will reduce cost of battery and will increase drive distance by safe energy. So also simplify thermal design, because when we are talking about power losses, even if it is relatively high efficiency, still about 160 kilowatt, it will be a lot of power losses to reduce. So essentially car makers looking today as gallium nitride as a next step after silicon carbide. We all know that silicon carbide had been successfully deployed by Tesla. And this will give opportunity to go to either for 10% of battery cost reduction, that it's a lot. We are talking about $100 per car here, or 20% of longer range. It's even more exciting today, especially in the United States, where driving range is a problem. How to do this with gallium nitride? I had been asked to make less marketing, so I tried to put more technological slides here. So let's look at how we can design gallium nitride for next wave. First, that inverter requires, that car requires, a high current per die. And we can achieve this high current per die. Here you can see example of actual inverter working. That's still 400 volt battery voltage. But here we are going with 140 amps peak for 2 days of 22 milliohm. That's not top, but that's evaluation board that we have today. So that's about 70 amps current per 18 milliohm die, which is successfully working. Next one that is required for inverter, which is a high threshold voltage. EMI and as from Nexperia and Transphorm talked about it. It's right. DMOD device together with auxiliary circuits. We are using direct drive, which is different from cascade. And you can see here that's an actual 5 volt. It's 5.5 up to 6.5 threshold voltage design because we are running fast switching of high current. So we are expecting some AMI and a high threshold voltage, at least as IGBT is expected. Next one that is important is to be able to easy parallel components. Car requires power. We are talking about, even for 800 volt, it will be high current. For 400 volt, as had been kindly noted, where will be mainstream for next 10 years, we are talking about 300, 600 amps per car, per inverter, so we want easy parallel this. On this example, you can see paralleling of 4 devices of 8 milliohm each of them, totally generating 900 amps with unprecedented low switching energy here. This is done on demonstration of this die. So this is a product not available, we do not plan it yet in discrete mode because it's really large die, 8 milliohm, working finely, and this is a demonstration module. Because we understand to make model and demonstrate for customers, it's expensive and long job. So this is what our R&D guys invented, made, tested, and anyone can test this unprecedented low switching energy together with very high current. I think that no other technology today is able to provide this level of performance for power level. Next one, which is critically important for inverters, low switching losses. At the same conduction losses, we need, it's just jump here, but we will make it back and go. Doesn't want to work here. So when we are looking on low switching losses per given RDS-on, first of all, you are welcome to look at a very good presentation of VisIC, that's a French institute. They presented it first time at PCIM. And this one, they compared different components specifically for inverter. They also came up with figure of merit, specially designed for inverters, which from my point of view as a physicist, it makes a great sense. RDS-on, it's a switching losses at elevated temperature. And here you can see that gallium nitride is as good as best of silicon carbide, with obvious lowest manufacturing cost that we all understand. And in addition to it, if you compare side by side, IGBT, silicon carbide, gallium nitride, same voltage, same current, you can see that silicon carbide is about 3 times better than silicon, which Tesla uses today. And gallium nitride is about 5 times better than silicon carbide. And that's a next wave in design. And here I can add that this is measured also on 8 milliohm die. And 8 milliohm die on the switching losses, we are responsible for models. We are doing models. We have own PDK. And you can see very nice coincidence of also thermal and switching losses, actual and the model, which is not simple to make for gallium nitride. We are very proud of it. And the last one is high robustness, high reliability. When we are talking about high reliability for this platform, D-Power 3 platform, we are talking also about very high blocking voltage. I believe, and I'm dealing with gallium nitride since 2000, building different devices. So what we have for this 650 maximal rating, blocking voltage is 1500. And as you can see, load line of these devices in actual inverter is about like this. It's not nice load line, but it stays well inside of actual safe area of device. In addition to it, we have critical parameters of a surge energy, which we know is a painful point of gallium nitride. Yes, we have short circuit protection working within 200 nanoseconds, but in addition to it, it's good to have high surge energy inherent for platform. This one is done by Virginia Tech CPES Center, which I think is the best place for power electronic in the world, probably after this place where you are present. And they measured and compared it after a million cycles of this dynamic breakdown voltage and high robustness. Our devices are stable in non-changing parameters. In addition to it, dynamic RDS-on, they had been plagued for many generations, especially for high-power devices. On this platform is less than 2%. That's a third-party results. So when we are looking on all this story, all these devices, I think I tried to show you how we designed on a very high level gallium nitride for inverters and high power. It's impossible to make in a 5 or 6 slide under 10 minutes, but we will be happy to answer on all your technical questions and give you great components to innovate in your power circuits. Came to our booth, came to our website. We will be happy to serve you. Thank you so much. Any questions?
Thank you, Tamara. Questions from the auditorium? It's quite auditorium.
That's a quiet auditorium.
They may come to your booth or contact you by email or through your website. I say thank you to the presenters. Thank you to the auditorium.